our discussion on this error detection and error correcting codes. So let me present my screen. Okay. Yeah, so this is that slide which explains the principle of error correction. So as you can see, if we wish to have single bit error correction, then we will have to ensure that the effect of a single bit error, on any code should be distinguishable from the effect of a single bit error on any other code. So that is what is depicted in this hypercube. So this represents the requirement for single bit error correction. All right. Now you will notice that if you have the provision for single bit error correction, you also have enhanced error detection. So if you look at this diagram, as you look at this diagram, let me pose a question to you. That is, how many bits of error detection do you think is possible from this diagram? How many bits of error detection do you think is possible from this diagram? Just look at this diagram. It is actually quite evident. Can some of you just examine this and try to give an answer? It's not too difficult. It's rather simple, in fact. So, yeah, who will suggest an answer with a justification? Someone? So, yeah, please speak up, because so someone who will answer? So should I call out someone's name? So let me call out someone's name. So Chinmay Jain.
Yes, sir.
Yeah. Would you like to just suggest an answer? Just look at this diagram. I hope you can see this diagram.
Yes, sir. I can see
Yeah.
it.
So this one, as I explained, this sort of arrangement allows a single bit error detection. Error correction. It allows for single bit error correction. So what kind of error detection? Do you think is possible from this?
Sir, 3.
Whatever be your answer, just try to justify it.
So because it is a two-step method, because we have to reach from 000 to 111. So we have to we are using 1-bit method. So we have to change one.
I will just correct you there. You don't want to reach 111, because if you reach 111, then you can't distinguish a correct situation from an erroneous situation, right? So
Yes, sir.
in the presence of error, you don't want to reach a valid code. You want to stop short of a valid code. All right.
Okay.
Do you understand this, everyone? So in this diagram there are two valid codes, 000 and 111. Okay.
Mm-hmm.
Now if you so the orange or light orange. So the sorry, this is pink. So this pink 000 is in a pink circle. So this and this one is, let us say, it's a blue circle. So this pink circle and blue circles, these represent two valid codes. And this lighter shades, these represent erroneous codes. Okay. So so as you, so what's an error? An error is simply a bit flipping. All right. So 0 becomes a 1 or a 1 becomes a 0. All right. So if you have so this light pink, these these indicate the possible codes arising from a single bit error on the code 000. All right. So if you have a single bit error on the code 000, you can have these three possibilities: 1000001 or 010. All right.
Yes, sir.
And you have also seen that on 111, if you have a single bit flip, you can have the codes 101110011. So as you can see that these sets are disjoint. So since these are disjoint, it is possible to, you have the information. You have not lost the information. See, you have to understand one thing. One aspect is that you should not lose the information, because if you lose the information, there is no way you can regain it. The other aspect is whether you can have an effective computing procedure. Okay, whether you can have an effective computing procedure. So the Hamming error correction that we showed last time, that actually gives you an effective computing procedure. Now, what we are showing now, this one is just indicating the minimum requirement, because if you go beyond this, then you lose information. If you lose information, you cannot possibly have a computing scheme which will allow you to recover that information. All right. So if you look at the same diagram, you will find that up to 2-bit flips from any valid code will still stop short of another valid code. Okay. So if you look at this, if you start from 000, you can see that you can allow 2-bit flips, any 2-bit flips. You will still not reach 111. Do you notice that? Similarly, from 111, if you start, you'll find that as a result of any 2-bit flips, you still stop short of all 000. All right. So, in other words, this code, I mean, this scheme which you have seen over here, this separation of valid codes, this allows for 2-bit error detection. All right. So, so can you generalize then? So if you have k-bit error correction, then how many bit error detection can you have? If you have k-bit, if your code allows for k-bit error correction, then how many bit error detection do you think should be possible? Can someone venture an answer? So should I call out any other name, or do you want to answer on your own? So Girish Kumar, do you want to answer? Girish Kumar?
Yes, sir.
Yeah, uh, 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 so suppose, yeah, so what do you think? If you have k bits of, if your code allows for k bits of error correction, then how many bits of error detection do you think should be possible?
Sir, K plus 1.
Why do you say k plus 1? So if you have k bits of error correction, then how many, that means you can allow k bit flips, right? So
Yes, sir.
you take any two valid codes. Okay, before I explain, no, your answer is not correct. So let me just ask someone else. So Devajoy Mukherjee, do you want to answer? Devajoy? Hello? Devajoy is not responding. Devanjan, would you like to try? Devanjan Shaha?
Yes, sir.
Yeah. So why don't you just try to answer? Suppose your code allows for k-bit error correction. So how many bits of error detection do you think should be possible? Yeah.
Sir, there are answers. There are a lot of answers in chat if you want to
Sorry?
check.
No.
Uh,
That's what I'm saying. You can maybe just answer. So it's better you because again finding out the chat box. Where is the chat box?
Sir, next to the participants button.
Yeah. Okay. Yeah. So someone has answered 2K. Yeah. At least I can see two answers. So 2K. So let me just explain. Yeah, 2K is correct. So at least so let me just try to justify why it should be 2K. Just a minute. I think can I start in the steps? Yes. Yeah. So I will use the same logic which is depicted in this diagram. So let us say that this is a valid code, all right, and this is a valid code. So you have k bits of error detection. That means you have, let us say, 1, 2, and finally you have k. Okay. So these are all invalid codes. These are valid codes. All right. These are valid codes. So, and let us say here also you have one bit, one bit. So these are all, bit errors. And you have, say this is k bit, all right. So, and if you want error correction, that means these should be disjoint, right? These two, because if they overlap, then you lose information. So if these are disjoint, you can trace all. Yeah, I think I'm getting an echo. Uh, yeah, if you are not speaking, please mute. Sometimes that can cause an echo. Okay. Yeah. Similarly, all of these should be, these two sets so that you can trace this. So these you want to trace to this and these you want to trace back to this. But if you see that for error detection, this is for error correction. Okay, this is, you want to trace back for error correction. All right. For error correction, you want to trace back. For error detection, you don't want to trace back. You just want to know whether it's a valid code or an invalid code. So you see that you have 2K over here. So if you have 2K bit flips, you still don't reach. You still stop short of a valid code from another valid code. So that is what you can see. So if your code allows for k bits of error detection, then it should support 2 bits of error correction. Okay. So I hope that is clear. These are all erroneous codes. All right. Okay. So let us just carry on. Okay. So yeah. So let us just see some arithmetic on the minimum number of bits required for ECC. All right. So let us say that you have got m bits of information overall, and you have got a total of n bits. Okay. So you have the scope of having p parity bits, right? You have got m information bits and a total of n bits. So you can have, let us say, p. If you have p parity bits, then of course m plus p should be equal to n. All right. So now when you have a single bit error, so each uh, for each valid code word, you have n patterns. Okay, you'll have n patterns. So you need to reserve n plus 1 patterns for each code. All right, you need to reserve, because for if you have got n bits, so yeah, so you'll have n patterns. All right, so you have got n patterns for 1 bit error and 1 valid pattern. All right. So you are reserving n plus 1 patterns for each code, and this is the uh, inequality that you need to satisfy. So with keeping all this pattern. So if you have got m information bits, so you will have 2 to the power you'll have 2 to the power m possible valid codes, and so many patterns are required, and all of those should be accommodated in n bits. All right. So if you just work out this arithmetic, you just do some simplifications, and you get this inequality. So if you put m equal to 4, then you want to find out the value of p. So you find that if you put p at 3, then you are able to satisfy this inequality. All right, you are able to satisfy this inequality. So that is what we have. We have, for this Hamming code, we have Hamming ECC. We have got four data bits and 3 parity bits. All right. Okay. So yeah. So I think we have basically studied this. Now let me just give you another diagrammatic representation of, suppose you have, you are using a code of 5 bits. All right. So, and if you want to allow detection of 1 bit of error, so if you look at this table, so in this table you find that there are 32 entries, right? There are 32 entries corresponding to the 5 bits, and if you take if you let us say if you allow 000 to be a code, so what you want to do is any code which is adjacent to that code, meaning that if you flip 1 bit, So when we say adjacent, we mean codes at a Hamming distance of 1. So you consider all codes at a Hamming distance of 1 from 0, 0, 0. So you don't want to, those should not be valid codes, right? So if you take say 0, 0, 0, so which of these are adjacent to, so this one is adjacent to this one is adjacent, this one is adjacent, and also this one is adjacent, right? So these are the 4 codes that you get by flipping a single bit, all right? So these codes you cannot allow. Now if you see, if you look at the ticked codes, you will find that all the ticked codes are 1 bit apart from, are 1 bit apart. In fact, these are exactly 1 bit apart. So what you can see is that you can, if you have 5 bits, if you have a code of 5 bits, you can use if you use 4 bits, then it is possible, you don't lose information. It is possible to detect single bit errors. Okay, so this is just a depiction of how you can have 1 bit error detection for a 5 bit code. All right, so yeah, so you can also say that if you consider this BCD, say in case of BCD, you don't actually use up all the codes. You have some spare codes, but if you do this kind of analysis, what you find is that you cannot have error detection in these 4 codes, okay, because going by the same logic. So with 4 with 4 bits, you can have you could accommodate error detection if you had only 8 valid codes, but here you have 10 valid codes, so you do not have enough spare codes to allow or spare patterns to allow for single bit error detection. So if I mean, so what that means is that if you want to do error detection in BCD, you will require 5 bits. All right, so with this we come to the end of this topic. So what I'll do is I will just discuss the lab assignment with you, because that is aligned that is aligned to this topic. So what we have here, so you can open this on your own browser. Maybe I'll just make it a little bigger and increase the magnification so that you can see it more easily. Okay, so the experiment is on single bit error correction with display. So first of all, what we have is so let me just show the overall setup. So this is your overall setup. So on this, so this is the sender, okay. This is the sender and this is the receiver. So on the sender side, you have got 4 bits of data. Okay, you have 4 bits of data and 3 bits of parity, as we have already seen. So maybe I'll just go back to So you have 4 bits of data and 3 bits of parity as shown in this diagram, adjoining diagram. And just hold on a bit. Sorry. Yeah, so you have 4 bits of data and 3 bits of parity. And so from this side, from the sender side, you are sending 4 bits of data and this 3 bits of parity. Now, it is possible, so as you are sending, it is possible, so we'll assume that you can have some disturbance, but the disturbance is not so much, uh, is not too bad, but you can have at most 1 bit flip, all right? So how do you model that disturbance? So the way we'll be modeling that disturbance is this way. So we will have, so if this is your data, and if you want to model the disturbance, so we'll put an XOR gate, okay? Put an XOR gate, and we'll have an input here, okay? So this is the data, this is data dash, and this is your, say, this is your, let us say the noise. So if, so D is equal to, D dash is equal to D if, and it is equal to, the complement of D if error is equal to 1. So that this is how you introduce the noise, all right? So what you have is, since you have got 7 lines, so since you have got 7 lines, so you'll have 7 XOR gates, all right? You'll have 7 XOR gates. Like that. So you have 7 XOR gates. And you can introduce noise in each of these, all right? So you can introduce noise here, or here, or here, so on. So you have got total of 7 lines, all right? So you have a decoder here. So what you do is, you have got a 3-bit, you can say noise selector. So you have got 7 output lines. So let us say that if you number these as 1, 2, 7, so here you can have codes from 0 to 7, all right? So you'll have, so 0 means all bits correctly transmitted. All right, and if it is I that is not equal to 0, that means line I, or for that matter you can say line I or bit I, whatever. Line I or bit I is flipped. All right, so you got to this. So this is a decoder. It's a 3-bit decoder. So using this 3-bit decoder, you can introduce noise in up to one line. So if it is 0, you don't introduce any noise, and for any other value. So now going back to this circuit, so you can introduce noise in any one of these lines. All right. Now on this side, what you do is you recompute the parity. So these are the parity bits which are sent, and these are the recomputed parities. All right. These are the recomputed parities, and this is the data. So now you basically follow this logic. All right, you follow this logic. So as you can see from this, you have so if you look at this table, you can see that so you have got parity bits at this position. So parity bit 1 affects so if you have so you're essentially computing this these 3 lines. So how do you compute these? So you have got, so you are getting, say, this is P1, this is P1 dash, all right, and you have an XOR. Then you have got P2 and P2 dash, so maybe I can just P2 and P2 dash, and I have another XOR here. And similarly, I have P3, P3 dash. So this one I can say that this is error in P1, error in P2, and error in P3, right? So these 3 lines are indicating whether I have error in P1. So basically, this is what I'm getting. So if it is 001, I mean, this will tell me whether I've got an error. So if it is 000, it means that there is no error. If it is 001, means there is error in P1. If this is 010, it means there is error in P2. If it is 011, it means there is error in P2 and P1. So like that. All right. So now I can consult this table to figure out whether I have a problem, all right, whether I have a problem. So which one I need to correct, all right. So if I go to the next page, let us say, so suppose I have these three lines, all right. So let us draw these three lines here. So let us say that this is EP1, this is EP2, and this is EP3, all right. So suppose all three are in error, all right. Let us look at if all three are in error. So how do I detect that all three are in error? This is how I can detect that all three are in error. All right. This represents this situation, right? All three are in error. So if all three are in error, I know that I got to correct D4. So what I do is I correct D4 here. How do I correct D4? This is how I correct D4. How do I correct D3? So D3 I know that P3, so P3 and P2 are in error. So P3 and P2 are in error. Alright, so P3 and P2 are in error. Alright, and P1 is not in error, so that I can indicate in this manner. This one is not in error. So this is how I can correct D3. So this is rather I can say D4 dash. This is D4. So this is D3 dash. This is D3. So this is the corrected value of D3. So now you can see I can correct D2 also. So D2 means here P3 and P1. So P3 so this is how I can correct D2. And finally D1, P1 and P2 are in error but not P3. So P1, P3 is not in error. These two are in error. Alright. So this is how I can correct D1. Alright, so this is my error correction circuit. This is how I can correct. And I really don't need to correct P1, P2. I'm just interested in this D1, D2, D3 and D4. If I need to, so I will normally not need to retransmit this, okay, because uh, the transmitter is already there. If I don't need to retransmit because the transmission is already happening here. So if I need to send it somewhere else, I can just connect this. I still assume that I have only a single bit error. Okay. I mean, okay. So unless I have to unless I have to repeat, I don't have to recompute the parity bits correctly. All right. So this is that ECC. That ECC which I showed you. This is that. This is that ECC. I mean, ECC is this plus plus this circuit. This together. This circuit. This is also part of your ECC. So this is part of your ECC. And this is this whole thing. This is also part of your ECC. Okay. So this is your ECC, and then there's the restore. So to make it a bit convenient, I mean, so we have also so this has also been given to you. This is the BCD display. So this this is called the 7-segment display. So 7-segment display. So maybe since you're not doing the actual lab, there are a few things that you should note. So what is the 7-segment display? So this 7-segment display, these are really some LEDs. All right, these are really some LEDs. So you can say it's you have an LED like this. So let us say this is also okay. So this is A, this is B, C, this is D, this is E, this is F, this is G. This is your 7-segment display. Now, when you connect this, there are two schemes. So one is that you can have a common anode. Okay. So if you have a common anode, then these are all connected. If you have a common anode. Okay, so if you have a common anode, the anodes are tied up and you connect this to your gate. Now remember, so basically, as you remember, if you go back to your, the circuits that we have done, your gate is, you have something like this. This is grounded, and then you have something over here also. So this is the output, which is also, connected to, or rather, it could be connected to, maybe this point. All right. So this gate will control this LED. So that means this is, say, VDD. All right. So if you want to light up this LED, you should provide a path to the ground. All right. You should provide a path to the ground. That means the output should be 0. All right. The output should be 0. This output should be 0. It should be low if you want to provide a path to the ground. That is one of the ways in which it works. There is another type of LED where you have, instead of, these, you might have the other terminals connected. So you can have a common ground. So it could be like this. It could be a common ground. So this one also needs to be connected. This one needs to be connected. So have I connected everything almost? All right. So this is, called common cathode. And the other one is called common anode. So these are two types of 7-segment displays that you get. It can either be a common anode display, or let us just say, it can either be a common anode display, or it could be a common cathode display. All right, it could be either a common anode display or a common cathode display. All right. So, in case it's a common cathode display, then you typically have, yeah. So in that case, you will probably have a circuit like this. So this is, and the output going to the anode. All right. All right. This is for driving A, and this one is for driving B. All right. So this is, so if you notice the particular arrangement that we have considered, so it can be, so we have not specifically told you. So in this case, so you can, so let me leave this choice to you. So you can, you can either choose a common anode display or a common cathode display. So in that case, your logic functions will be just, the complement. Either you will say, if your logic function synthesizes A, then it will be common cathode. If it synthesizes A bar, it will be common anode. So I'll just leave it to you. Some of you, some of the groups can do common cathode, some of the groups can do common anode. All right. I'm not. I don't want to tell you, who should do what, but among yourself, just try to ensure that all of you don't do the same thing. All right. So this is how 7-segment display works. For some technologies, actually, transistors are better at sinking more current than sourcing. So in some situations, this common anode is more convenient. Where you try to sink the current from the output to the ground. Yeah. So that is about the common anode display. So I think we have, so this is the setup that you have. So as you can expect, your, when you do this experiment, as you, as you, change the, as you change the, the input to the decoder, your output should remain fixed because you are able to correct any single bit error. So that is really what you need to demonstrate, that as you introduce noise over here, so either you will have no noise or you will have noise in at most one line. So under all circumstances, your display should remain invariant. That is what you should be able to demonstrate. All right, okay, then the experiment has already been put up, so you can work this out in for your laboratory. All right, so we'll stop here now. All right. In case you have any questions.